All right, welcome to the deep dive. We're all about cutting through the clutter, getting straight to what matters. And today we're going deep on something that's, well, it's kind of behind the scenes, but it's really at the core of how so many decisions get made.
Yeah, we're talking model risk management.
Uh-huh.
Might not sound super exciting at first glance, but trust me, it's a big deal, especially, well, everywhere, but particularly in finance and tech.
Definitely. And we've got some really great sources lined up for this. We're going from the basic concepts all the way to seeing how this plays out in real life using actual loan data and Python code.
Exactly. Think of it like we want you to walk away not just knowing what model risk management is, but actually getting a feel for how it works in practice.
So, okay, model risk management. Let's break it down. What is model risk, really? I mean, what are we talking about here?
Well, it all comes down to models. And I don't just mean like super complex AI stuff. It could be an algorithm predicting stock prices, sure, but it could also be, a spreadsheet you're using for your budget.
Oh, okay. Yeah, makes sense.
So model risk is basically the risk that those models, whatever they are wrong, or that they're not used right, which can happen. Maybe there's a flaw in how the model was built, or maybe it wasn't tested thoroughly enough.
Or maybe someone's using it for something it was never designed for.
Exactly. And the point is, when models go wrong, well, the real world feels it. It's not just theoretical. You can have financial losses, operational messes, even damage to a company's reputation.
Big consequences. So it's serious business. Now, are there rules around this? Is anyone, keeping an eye on things to make sure models are being managed responsibly?
Absolutely. Especially in finance, the regulators take model risk very seriously. In the U.S., we have the Federal Reserve, and they have this guidance called SR 11-7. It's like the framework for how financial institutions should handle this whole model risk thing.
Okay, so what does SR 11 to 7 say? What are the key points it lays out?
It's built around three main pillars. The first is model development, implementation, and use. So it starts from the very beginning, like how you build the model, what goes into it, and then how it's actually put into practice.
Right, and who's using it within a company and all that. Makes sense. So build it right and use it for the right purpose. What's the next pillar?
Pillar number two is model validation. It's all about testing, checking, making sure the model does what it's supposed to do, and spotting any weaknesses.
Kind of like a quality control check for the model.
Yeah, exactly. You got to put it through its paces. And then the third pillar is model governance and oversight. So this is about having the right structures in place, clear policies, who's responsible for what. It's about making sure there's accountability.
So those are the big three. Build it right, test it thoroughly, and then have a system to make sure everything stays on track.
Got it. Now, within those pillars, I know there are more specific areas to focus on. What are some of the key things people need to pay attention to when it comes to managing model risk? For sure. One of the most important is model documentation.
Documentation. Sounds a bit, boring. Like paperwork.
Well, it might not be the most glamorous part, but it is absolutely essential. Think about it. You need a clear record of every model you're using, what version it is, what it's supposed to do, who's in charge of it, how it's being used.
So anyone can come in and see exactly what's going on with the model.
Exactly. And this includes things like documenting all the assumptions built into the model and how any special features were calculated. Like if you have a variable called estimated credit score, you have to explain exactly how you came up with that score from the raw data, no magic numbers.
Transparency is key, so that's documentation. Now, what about validation? We talked about that earlier. What actually goes into making sure a model is valid?
So model validation, there's a lot to unpack there. But a core idea is testing the model rigorously, really understanding its strengths and weaknesses. There are a bunch of techniques for this. One is called cross-validation, and specifically in our source material, they use something called stratified k-fold.
Yeah. Stratified k-fold. That sounds intimidatingly technical.
Don't worry, the concept is pretty straightforward. Imagine you take your data and split it into, say, 5 groups. Then you train the model on 4 of those groups and test it on the 5th. And you do that for every combination. So each group gets a chance to be the testing group.
Okay, I get it. It's like giving the model a bunch of mini exams to see if it consistently does well.
Exactly. And the example we have showed an average AUC of around 0.7 from this cross-validation. AUC, that's area under the curve, by the way. It's basically a single number that tells you how well the model separates the good stuff from the bad stuff. The higher, the better.
So 0.7, is that good?
Well, a perfect score would be 1, and random guessing would be 0.5. So 0.7 is actually pretty decent. It means the model's doing something right. It has predictive power.
Nice. All right, so cross-validation, what else is there in the validation toolkit?
Another big one is backtesting. That's where you take the model and you see how it would have performed on past data. Like if you built a model to predict loan defaults, you can run it on data from a few years ago and see how well it would have identified the loans that actually did default.
Oh, interesting. So you're basically testing it on historical data to see how it holds up.
Right. And in our example, they use a variable called day/publish as a way to figure out roughly when loans were issued. Then they split the data by loan year. And from the backtest, they got a recall of 0.22 and a precision of 0.14 for predicting defaults.
Those numbers seem kind of low.
Yeah, so recall tells you out of all the actual defaults, how many did the model correctly identify? And precision is out of all the defaults the model predicted, how many were actually defaults. So 22% recall and 14% precision. That means this model is missing a lot of defaults and making quite a few false alarms. Important takeaway. A model can look good on old data, but be totally unreliable in the present.
So continuous monitoring is key.
Absolutely. There's also sensitivity analysis. This one is about, tweaking the input values a little bit and seeing how much that changes the model's prediction.
So like if you're predicting loan defaults, you might change the loan amount and see how that affects the predicted probability of default.
Exactly. It helps you understand if the model is overly sensitive to certain factors or if there's a point where changing an input doesn't really make a difference anymore, which is called feature saturation.
So you're kind of like poking the model to see how it reacts.
Pretty much. Then there are sanity checks. These are more like common sense tests. In the example, they shuffled the target variable, which was prepayment risk.
Shuffled, like randomized it.
Yep. They scramble it up and then retrain the model. And if the model still performs well on that shuffled data, well, that's a big red flag.
Because it means the model's not actually learning any real relationship, right? It's just memorizing noise.
Exactly. And finally, there's model calibration. That's about checking if the probabilities the model spits out actually match up with real-world frequencies. They use calibration curves, and it turns out this model was fairly well calibrated for low-risk loans, which means for low-risk cases, the probabilities it predicted were pretty accurate. Lots of ways to put these models to the test.
Wow, so many ways to poke and prod and make sure the model is doing what it's supposed to do. You mentioned overfitting earlier, where a model kind of learns the training data too well. Why is that such a bad thing?
Overfitting, it leads to what's called generalization risk. It's like, imagine you're studying for a test by just memorizing the answer key. You might ace that specific test, but if the questions are even slightly different on the real exam, you're in trouble. Same with models.
Makes sense. The model needs to be able to generalize to apply what it's learned to new situations.
Right. If it's overfit, it's basically memorized the quirks of the data it was trained on, but it hasn't really learned the underlying patterns, so it can't generalize. And the real world is always throwing curveballs. The data never stays exactly the same.
And speaking of the data changing, that brings us to data drift and concept drift. These sound like things that can happen over time, right?
Absolutely. So data drift is, well, the data drifts. Its statistical properties change.
Can you give an example?
Sure. Imagine you've got a model predicting loan defaults, and you trained it on data where the average income of your borrowers was, say, $50,000. But then over time, the average income in your applicant pool drops to $40,000. That's data drift.
The data the model sees in the real world is different from the data it was trained on.
Exactly. And then there's concept drift. That's when the underlying relationship between your input features and the thing you're predicting changes.
So like maybe a certain economic indicator used to be a really strong predictor of loan defaults, but now it's not as reliable anymore because the economy has changed.
Exactly. The rules of the game have shifted.
So how do they illustrate data drift in the material we have?
Well, in the code, they actually simulate data drift.
Yeah.
They artificially change some of the data, like increasing income and credit amounts, and then decreasing an external credit score. And when they run the model on this new grifted data, the performance drops. They even show how the distributions of these key features like AMT credit, anti-income total, XD source 2, all shift because of the drift.
A very clear demonstration that a model can become less accurate as the data changes around it. Okay, last but not least in our core concepts, we have model governance. What does good model governance look like in practice?
Model governance is like it's setting up the whole system for how you manage models within an organization.
Right, so it's not just about one model. It's about having the right framework for all models.
Exactly. So you need clear roles and responsibilities. Who owns each model? Who's accountable if it goes wrong? You need policies and procedures for everything. from development to validation to how the model is used. And a big part of good governance is independent review. Having someone else check the work, catch potential biases, make sure everything's above board.
So it's about having checks and balances, making sure models are used responsibly. Okay, let's shift gears a bit and look at the practical side of things. Our sources include some Python code that actually analyzes loan data. What are some of the first things they do with the data?
They use the pandas library, which is a really popular tool in Python for working with data. And they do some data manipulation, creating new features from the raw data, features that might be more useful for predicting risk.
So, like, instead of just using someone's income, they might calculate their debt to income ratio.
Yeah, exactly. Or they create a loan-to-value ratio, which is the size of the loan compared to the value of the asset it's secured against. And they calculate an implied interest rate, approximate the loan term years, and even create an affordability index. They also use these new variables to create a risk category where they segment loans into different risk levels based on things like their LTV and DTI.
They're basically extracting more meaningful information from the raw data.
Yeah, that's feature engineering.
I also noticed they took a subsample of the data, like they reduced it down to 10,000 rows. Why do that?
That's a good question. They did that mainly for speed. Working with 10,000 rows is a lot faster than working with millions of rows. And for some tasks, like figuring out which features are most important, a smaller sample can actually give you more stable results. But there are definitely times when you don't want a subsample.
So when would subsampling be a bad idea?
Well, if you're analyzing things like model drift over time, or if you're looking for those rare but really important events like a very specific type of fraud that doesn't happen often, then subsampling could make you miss those crucial data points.
So it's a trade-off. Sometimes a smaller sample is fine. Sometimes you really need all the data.
Right. It depends on the task.
Okay. Now, they also created this estimated credit score. How did they do that?
That's another example of feature engineering. They're basically building a simplified credit score using the data they have. So they take things like how long someone's been employed, a measure of their past credit behavior, and those ratios, we talked about debt to income and loan to value, and they combine them using a formula to get a score. But it's important to remember this is just an estimate based on the specific data in this data set.
Right, it's not like an official credit score from a credit bureau.
No, exactly. Then they define their target variables, what they're trying to predict. In this case, it was prepayment risk and default probability.
So how did they determine those?
For prepayment risk, they basically said if the loan term was less than 2 years, then it's considered high risk for prepayment. The idea being that short-term loans are more likely to be paid off early. For default probability, they used the risk category they created. If a loan was classified as high risk based on its LTV and DTI, it got a default probability of 1, otherwise it was 0. These are just examples of how you might define your target variables. It really depends on what you're trying to achieve.
Makes sense. So they've got their data prepped, their features engineered, their target variables defined. Now they get to the fun part, building a model. And one of the coolest things they did was this feature importance exercise using a random forest classifier. Can you tell me about that?
Yeah, so this is where they try to figure out which of the input features are actually driving the model's predictions, like which factors are most important in determining whether a loan defaults or not. They used a random forest model, which is a really powerful machine learning algorithm for this kind of task.
Okay, so what did they find? What features were most important?
Well, this is where it gets interesting. The most surprising finding was that the number of days since the borrower last changed their phone number, days last phone change, was really important.
Wait, really? That seems kind of random. What about, like, income? Wouldn't that be a big factor?
You'd think so, right?
Yeah.
But AMT income total actually had a relatively low importance.
So changing your phone number is a bigger red flag than how much money you make. That's wild.
It is kind of counterintuitive, but think about it. A recent phone number change could be a sign of instability, maybe even fraudulent activity. And sometimes, in credit risk, these behavioral signals are really strong predictors.
Interesting. So it's not always the obvious things.
Right. As for income, the thinking is that its impact might already be captured in those engineered features like the debt-to-income ratio. So the model's basically saying, yeah, income matters, but I already have that information in more useful form through these other variables.
That's fascinating. The model's finding these subtle connections. So what were the other top features?
Well, the top 15 were a mix of external credit scores, demographic info, loan characteristics, and those engineered financial ratios we talked about. Things like XC-Source 2, days birth, EGMT credit, the usual suspects.
Okay, makes sense. Now, to really understand how those features are affecting the predictions, they use something called SHA values. Can you explain what SHA values are in a way that, a normal person can understand?
So imagine you've got a specific loan applicant, and the model has made a prediction about whether they'll default.
Yeah.
SHAP values basically tell you how much each individual feature contributed to that prediction. So you can see that for this particular person, their low credit score really pushed the model towards predicting default, but their long employment history pushed it in the other direction.
So it's like for each individual prediction, you can see which factors were the most influential.
Exactly. It's like peeking inside the black box of the model and seeing how it's making decisions. Very cool stuff.
So we've covered a lot of ground. We've talked about what model risk management is, why it's important, some of the key techniques, and even seen a bit of code in action.
Yeah, we've gone from the high-level concepts all the way down to the nitty-gritty.
And hopefully this has given our listeners a solid foundation.
Absolutely. Because this stuff is becoming increasingly important no matter what field you're in. More and more decisions are being made with the help of models.
So understanding the potential risks and how to manage them is crucial. And on that note, here's something for our listeners to think about. Take a moment and think of a decision in your own life or in your work that relies on some kind of model. It might not be called a model, but it's some system that uses data to make predictions or guide choices. What are the potential risks there? Could it be wrong? Could it be biased? How could you apply what we've learned today to evaluate that situation?
It's worth considering because models are everywhere. They're shaping our world in ways we don't always realize.
Food for thought. Thanks for joining us for this deep dive.